Okay, so before we continue with the protein separation characterization, I have a couple of things and reminders and announcements, I would say. So first, I always try to like to give statistics so people know where they are and how was the exam in general. So I don't know if you guys can see, those of you that are on Zoom, but the exam has a very good average, 81.5. Usually this is one of the good averages we've seen. So if you scored around there or higher, that's pretty good. A little lower than that, that's fine too. Um, so even if you didn't do well, don't panic. You know, in food analysis, it's not a midterm and a final. You have a lot of opportunities to get points and a lot of extra credit opportunities. Don't panic, but if you have any questions on how to study for the final, please reach out to me and I'll help you out. Also, remember, we do have a review session. I was asked today if we're going to have a review session for the final. We do, and it's the last week of classes during the lab period. So we'll have 15 of you each in lab period, so we have enough time to discuss questions and talk with each other. You are expected to attend. I will be circulating questions to practice before the review session, and some of these questions will be actually on the final. So this is very important that you attend that review session in the last week of classes. So the other thing, I thought about the quiz too. I can't have it on the 4th. I said we're going to move it from the 2nd to the 4th. I talked to the Monday group class. No, today is Wednesday. I talked to the Wednesday group today in the lab because I got a request to change that date for the quiz because there's the approximate analysis report due on the 2nd. So I thought, okay, we'll do it on the 4th, but I can't do it on the 4th because I have a celebrity coming to give you a lecture on the 4th. A food analysis celebrity, not not a Hollywood celebrity, no. And it's a surprise, so I'll announce that visitor later on in an email. So I don't want to have that quiz, so you will not be paying attention and you'll be distracted. So I don't want to do that on the 4th. So I'm suggesting that we have the quiz on Monday, the 7th, which would be after the weekend. Do I hear any objections? I want to make sure that everybody on board, you can chat in the chat box if you object. But that means everybody's going to see who's the objector. Is, oh yeah, you can send to Laura privately if you object. Good idea, works for me. Great. But if you, for any reason, object, um, we will work something else out because it has been scheduled for December 2nd. So I need to make sure that it's fair for everybody. So Laura, if you get any objection privately, you let me know later on. I will. Yeah, none now, but someone just wanting clarification that it's during class time. Oh, so thank you. So the clarification on that, we do have a lab on Monday, but it's going to be short. So it's a virtual lab, but it's going to be short. I'm not sure, maybe an hour, hour and a half virtual lab. So I'm thinking that we open the quiz at 12. So we have half an hour or so, or even a little more before lecture time. So I reserve lecture time. So you can take the quiz before lecture time. So, and I don't think the Wednesday group have anything on Monday prior to the lecture. So hopefully there's no conflict by opening the quiz for everybody at 12 noon. Again, if you have any objections, you can send directly to Laura in private chat if you have any objections to 12 p.m. on Monday. So it shouldn't take more than half an hour. It really needs 20 minutes, but we'll open it for half an hour. And if you need more time, we would still have additional time before actual lecture time. So if that is okay with everybody, that's what we will do. Otherwise, Laura will tell me if there's any objections with that. Okay, one last thing. I opened another extra credit opportunity under this week's, I don't know if it's week 12. It's for protein characterization, separation and characterization. And this practice set is again for a +5 points, extra credit. So two birds in one stone. First, you practice and learn the material. Second, you get extra credit. Now, when is it due in the sea of things due? Laura and I thought about uh, December 4th, Friday, by 5 p.m. So kind of spacing out things that are due for you. Okay. Again, this is not an obligation. This is an opportunity for you to study early and gain extra credit. Okay, let's see. I think this is all my announcements. So we can continue with this lecture today. Hopefully I finish. If I don't, we'll finish it on Monday. But just to remember where we were at, I had few slides introductions for this topic. And let's review together what is protein separation utilized for. You can look in your notes. You can try to remember on your own. Um, Abby? Yes, producing protein isolates and concentrates, that's a big deal in industry, especially nowadays. So protein separation, isolation, purification can be for industrial reasons to produce ingredients of different protein purity. That's one. What else is there? Uh, yes, impact of processing on structure, absolutely. So impact of not just processing in general, but impact of extraction procedures, functionalization, of processing, thermal processing, drying, using solvents. So how would that impact the protein? So that is also important. Uh, um, So allergen testing and nutrition, we do that as part of protein characterization, but not necessarily separation. Um, Mm, Maybe if we want to do the amino acid composition of a particular protein, yes, we can separate it from the lot. But sometimes you get a flour sample that has protein, you can still do amino acid analysis on the flour and you can still get protein digestibility within the flour. You don't necessarily need to isolate unless you need to look at the particular protein fraction within the matrix, multiple proteins in there, and you want to isolate one of them and assess them, then yes, you do that. So which brings me to the third one, which is we separate, isolate so that we understand the protein better, specific protein better, we characterize it, we understand it better, so we have to separate it from the mix. And sometimes we purify enzymes, we purify antigens, antibodies. These are all proteins, so we purify them to be used in assays and so on. We talked about few methods of separation. We're not done yet. We stopped somewhere. So, what do you remember what we talked about? Salting out. Yes, we're using the salt to precipitate the protein based on their net charge. Very good. Uh, Isoelectric precipitation, separation by adsorption, differential solubility. Very good. So, yes. So, there are so many different methods. Differences in solubility is a big one, whether based on their denaturation temperature, whether based on their isoelectric point, their solubility in different solvents. So yes. Okay, very good. Let's continue with methods of separation. So we are still, well, let's talk about adsorption. I don't know if we talked about, we didn't talk about adsorption. We talked about solubility, separation by differences in solubility. So adsorption, basically we use chromatography. So the protein adsorbed to different matrices, and we can utilize this function to separate them. So for example, one, if you want to remember, again, I got a question today about what's going to be on the final. And it is cumulative, yes, but don't let your brain go too much information. So I will focus on the final on everything after the midterm. So you'll get very specific questions for everything after the midterm. But chromatography, spectroscopy, we learned it in the first half. It's going to continue with you. So you really need to review those. Sample preparation is important chapter. Data analysis is important chapter. So these are kind of basic information that you need to know that will help you in the next chapters, but I won't be asking specific questions about those, but they need to be in your background. So here, for example, you need to remember anion and cation exchange, because you need to be able to give me that example for protein separation and understand it. So, okay, so anion versus cation exchange, that depends on the charge on the protein and the pH of the system, because proteins can change charges based on the pH of the system. So based on and their isoelectric point and the pH of the buffer, they can be either negatively charged or positively charged. So based on the conditions we're running the samples in, we can either have a cation exchanger or an anion exchanger. This picture here is an anion exchanger. So on your column, you have positively charged groups, and you have your negatively charged proteins interacting with the positively charged groups of your stationary phase. And the more ion valence that protein has, the more interaction it will have with the column. So that's kind of a review of your ion exchange chromatography. So specifically for proteins, the resin that you use or the stationary phase that you use is a polysaccharide based, because they form large pore sizes, and proteins are large molecules. So that's why you have a polysaccharide base with the OH groups of the saccharides derivatized to carry either a positive charge or a negative charge. So here in red, I say pi of a protein is important. That means the isoelectric point of a protein is important. You do not want to run the isolation at a pH where the protein is not soluble. It will just precipitate and not separate. So you want to make sure that your buffer pH is outside of the range of the isoelectric point. So that is an important consideration. Now, this is one of the questions that is actually in the practice packet. But I want to solve this together with you to emphasize the charge of the protein and also the isoelectric point and avoidance of isoelectric point. So let me just ask you this to see that you all know before you try to attempt to answer this question. What would be the charge of a protein above its isoelectric point? Would it be negatively charged or positively charged? Above its isoelectric point. At a pH above its isoelectric point, would it carry a net negative charge or a net positive charge? Okay, so you're getting somewhere there, Abby. You're having the right thought. But let's think about your thought here for a second. So you are very true. We're increasing the OH minuses in the solution. So what happens? You have an amine group in proteins, right? You have multiple amine groups in proteins, and they have a tendency to carry proton plus one. So when you increase, and then you have a carboxyl group, which is COOH. The carboxyl group is going to readily give you a proton when you titrate with a base. It's an acid group, so it's readily going to give you its proton. But the amine group is not, it's going to hold on to its proton longer. Okay, so, but if you titrate with OH, the carboxyl groups are going to give you a proton. When the carboxyl groups give you a proton, it becomes COO minus. Increase the pH even more OH groups, it's alkaline now, it's pH 10. The amine groups now reluctantly are going to give you their protons as well. So you will end up getting even more negative charge. So above the isoelectric point, carboxyl groups readily give you protons, so become negatively charged. Even more alkaline conditions, your amine group is going to give you a proton, and the whole net charge is going to give even more negative. Titrating with an acid, that means you're decreasing the pH below the isoelectric point. You're continuing adding HCl, let's say that's your acid. So now your carboxyl groups are going to retain their hydrogens. They're going to take protons, and the amine groups already protonated and positively charged. So the protein will be positively charged under its isoelectric point. The net positive charge increases with more acid conditions, and the net negative charge increases with more basic conditions. Okay, so isoelectric point, zero charge. Above it, it's going to be negatively charged. Below it, it's going to start being positively charged. Okay, with this in mind, let's think about that now. All right, most of the proteins in a mixture, okay, you have a mixture of protein and you want to isolate a particular protein. So most of these proteins in this mixture has isoelectric points between 6 and 6.5. But the protein that you want to separate from the rest has a pi of about 4.5. You want to separate this protein from the other, this particular protein, by ion exchange. Would you use an anion or a cation exchange resin? At what pH would you use for your buffer? Why? Which proteins will elute in the wash? So thinking about what I just said about isoelectric points and the charges above and below, and you want this one particular protein, so where would your gut feeling tell you to start? Anion, cation, what pH? Who said? Cation. Okay. So that means your ions are going to be positively charged. Your proteins will be positively charged. Is that what you want? Which pH were you thinking? Yes, cat. That is correct. Anion exchange, maybe 5. Yes, 5.5 is correct. Why? At pH 5 or 5.5, the proteins that you're not interested in will be positively charged. The protein you're interested in will be negatively charged. So if you run the system at that pH and have an anion exchange, those proteins that you don't care for and are positively charged, they will elute with the solvent front. They will not interact with the column. Because the pH is 5. For them, pH is 5 is under their isoelectric point, so they will be positively charged. However, pH 5 or 5.5 for the protein of your interest is above the 4.5, so that will be negatively charged. So if I use anion exchange, only this protein of interest of mine will interact. The rest will just go out with the wash or your solvent front. That's what the wash means, solvent front. Okay, is this clear for everybody? Do I need to repeat anything? Okay, perfect. So how will you elute the protein? Now we got rid of the proteins we don't care for, and my protein of interest is interacting with the column. Now I want to let it out. I want to let it out in a decent amount of time. So what do I do with my pH or something else? Yes. Yes, Anastasia. So the proteins with at pH 5 or 5.5, those that I don't want will be positively charged. So they won't interact with the column, they go with the wash. But now we are asking about how do I elute the protein of interest? Yes, Sam? We do not want to use isoelectric point at all. We don't want to come near it. We do not want to come near it because the protein will precipitate, it will not come out. Will just precipitate somewhere on the column and not come out. Okay, so we don't want to use isoelectric points. So we go away from it. One way you can do is increase the pH actually. So if you increase the pH, your protein now continues to be negatively charged, but your column won't. You will have OH groups competing now. OH minuses are going to be competing to interact with the positively charged stationary phase. So then they block the positive charge on the stationary phase, then your protein will no longer interact and will come out. That's one way. Or you can increase salt concentration. Increasing salt concentration also helps because then you also have the counter ions that would compete to interact with the column. Okay. We talked about hydrophobic interaction chromatography when we covered chromatography, and this is very unique to proteins. So again, as a refresher, what happens in hydrophobic interaction chromatography, when we solubilize the sample with salt, the protein charges are blocked or are shielded. So then interactions will be via hydrophobic interactions. So the protein will interact with the hydrophobic matrix or stationary phase in the presence of salt. If I want to take them out of the column, I would then reduce the salt concentration. So the most hydrophobic protein on the surface, when charges are blocked, will interact the most. The least hydrophobic protein on the surface will interact the least. Okay, so this is just a chromatogram that we usually get when we are separating protein, and we use this methodology actually very commonly to separate protein from carbohydrates. So if we have protein and carbohydrate in the system, and we just want to remove the protein or isolate the protein, we can run the solution through hydrophobic interaction chromatography. In the salt time, when we're running salt, all of our carbohydrates will elute, will come out. And then when we change to water, our protein comes out. Here we don't care to separate the protein, we just want from it themselves, like if you have multiple proteins, we have to change the salt in a gradient format to separate the proteins themselves. But if I just want to collect the protein and separate it from carbohydrate, for example, or other components, I can run the salt, all other components that are non-protein will leave the column and the protein will come out with the water and I can collect my protein. Affinity chromatography is also commonly used, but it is used specifically to purify certain components, antibodies, antigens, enzymes. So it's very uniquely used for purification of a very specific protein. Again, you remember from chromatography that you can have those ligands. Ligands are these functional groups on your stationary phase, those triangles They bind very specifically to your protein of interest in this case. So if we are wanting a specific protein, we can get an antibody that is specific for this protein and have that antibody be your legend here or ligand. So then everything else will not interact, and only the specific protein or antigen, if we're looking for a specific antigen, will interact. If we are purifying enzyme, we have enzyme inhibitors as those ligands. If it's non-specific, for example, we're separating glycoproteins, we can have those triangles be lectins. And the way we let them come out of the column after interacting with the column is by changing the pH or salt, because then we change specific interactions. Or we can have in the mobile phase ligands similar to the ligands in the stationary phase. Then they will interact with those free-flowing ligands in the mobile phase, and they will leave the column. Separation by size. There's so many different methods we use that are based on separation based on the size of the protein. A very common method we use very commonly in our lab specifically is dialysis. So dialysis, what we do it to remove salts basically, or small sugars. So let's say we isolated our proteins, and we know that either we isolated using salt solution or we isolated by changing the pH that caused production of salt. When you increase pH and decrease pH by HCl or NOH, then you get NaCl, and you don't want any salts in your isolate. So what you do here is very simple. We use dialysis tubing. So here is a container that has a very long tube, kind of like a skin of a snake. So it is very wrinkled, and you usually take as much as you need. So you take out something like this from that tube, you open it up, and it is a tube where you have to close it from one end and fill in your solution of the protein. And usually you cut as much based on how much milliliters of sample you have. So there is calculations that tells you how long that tube should be based on the diameter of the tube, how long it should be if you have whatever 100 ml sample or whatever. You fill in your sample and then you seal the top as well. So you end up with a tube as you see here in the picture. So you seal this and you put it in a container, preferably a large container when you have something like this. You need at least a bucket that you can have 5 liters, if not more, of water. So what happens in dialysis, it's an equilibrium process. So the tube has pores. So it's a porous material. And every tube comes with different size of pores. So in this particular case, this is a common one we use in the lab that has about 3.5 kilodalton cutoff. So, or 3,500 Dalton. So everything smaller than 3.5 kilodalton can basically go in and out the pores, right? Because the pores allow these to go in and out. So sometimes you can have a dialysis tube that is 1 kilodalton or 2 kilodalton, 3.5, 5. You can choose based on your application or what you're trying to retain inside of the tube. What we're trying to retain inside of the tube is often your protein that is higher than 3.5 kilodalton. So what happens then, you will get diffusion based on the concentration. So inside the tube, you have high concentration of salts, let's say, or small sugars. Outside the tube, you have water. So you go from high concentrated area to low concentrated area. And after a certain period of time, you reach equilibrium. No matter how long you keep it, once equilibrium is reached, you cannot reduce anymore the salt concentration or the sugar concentration in your tube. So we change the water. So we empty the bucket and we put fresh water in there. So we continue doing that until the last equilibrium we do, you have very small amount of sugar or salt remaining. You will never get to a zero because it's equilibrium. It's going in and out. So once you reach to an equilibrium where it is desirable, for us, for example, when we produce protein isolate, I don't want to see salt above 5% or 4%. The lower, the better. So we reach to an equilibrium where we're happy with, and we say, okay, this took 5 washes. Fine, took 5 washes. I reached the purity I want. So again, this is a very common procedure, especially used after isolation with salt or after potential of having salt. Sometimes we just want to remove small sugars to prevent Maillard reaction or remove reducing sugars. So that is another way or use. Um, what happens since water can go in and out too, right, at the pores. So sometimes you end up having bulging. That means more water is inside of the tube and it bulges and almost going to break off. So what we try to use are tubes that have polyethylene glycol layer on it to prevent excess water from going inside of that tube. Okay. It's kind of like blocking the water from going in because um, it's immiscible with water. It does not like water. Another separation by size, which is also commonly used in the protein world, and actually Gary Reinexis is using this right now for his protein flavor interaction work, which is very fascinating. So he put his protein with the flavors, small molecular weight flavors, and he wants to determine how much of these flavor compounds interacted covalently with the protein. So when you interact covalently with the protein, they stuck to the protein and they stuck with the large molecular weight protein. Free flavors can be separated from the protein and the flavor that interacted with it. So how does he use this technology? So what it is basically a tube and it comes in different shapes and sizes. Inside of this tube, I don't know if you can see here, I couldn't find one in my lab to bring for show, but you have here a membrane. So you put your sample on the top. And then there is a membrane here that separates it from the bottom of the tube. That membrane can have pores. And these pores can also be uh, 1 kilodalton, 3.5 kilodalton, whatever size that you want to separate from each other. So let's say it's 1 kilodalton. Then let's say Gary put his protein and flavor components that interact together on the top. Then you spin it down. So you apply pressure and centrifugal force. Anything less than 1 kilodalton in size is going to go through your membrane and go to the bottom of that tube. Okay. Then any flavor compounds in Gary's case that didn't interact with the protein will go through to the bottom of the tube. Any flavor compound that reacted with the protein will remain in the upper part of the tube with the large molecular weight protein that doesn't penetrate through your membrane. So you separated in this case, or Gary separated in this case, the flavors that did not react with the protein. Now he can tell how much of the flavor compounds reacted with the protein, if that's the research that you're doing. So that is very good way of isolating. Another example, if I have protein hydrolysates. So I take my protein, I put an enzyme, I break it down into peptides. And I want to characterize only the peptides that are less than 3 kilodalton in size because these are the bioactive peptides. So I can use another tube with a membrane cutoff of 3 kilodalton, put my hydrolysate on top, spin it down. All my small peptides will go down into the tube, and I can take the small peptides, separate them from all of the large peptides, and continue my analysis that way. Okay, so that's a very useful technique, and the membrane technique is not only used for research. So all of these examples I showed you with these tubes of different sizes, this is all for research. Now, what about producing an isolate? Protein isolate, protein concentrate, and you want to separate different components. You can also use membrane and applying pressure. We have a unit in our lab. We produce our ingredients on a larger scale where our protein solution with the salts or sugars or what we have is pumped through a membrane, a filter membrane. And then here in that disk, we can put in our filter membranes with different sizes and separate the protein. Protein becomes retentate. That means the protein that does not go through the pores, or the substance that doesn't go through the pores, is our retentate. So this is done on a large scale in industry. So you have membrane separation in industry as well to produce concentrates and isolates of protein. So we have different levels of the membrane pore size. So based on the pore size, you can have microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So here's a table that is an example for a separation of components in milk. So there are so many different components in milk, and there are so many ingredients that can come out of milk. You have the protein, you have the lactose, you can have the salts. So you can break down the milk system into so many different components. And you can do that based on the particle characteristics, size, particle size, molecular weight, characteristics. Is it an ionic like salt? Is it a molecule? Is it a macromolecule like a casein micelle? Is it cellular like a bacteria? So for example, based on the sizes, you can get traditional filtration, microfiltration, ultrafiltration. So it gives you the range of the size here, nanofiltration or reverse osmosis. To see it in more animated way, so let's say this is your milk. In milk, you have bacteria, you have fat, you have protein, you have lactose, you have minerals, and you have water. Okay, so if I pass the milk through microfiltration, the retentate, so the arrow is going left here, means that bacteria and fat will be retentate. That means they won't go through the filter. So in microfiltration, protein, lactose, minerals, water go through, and we can get rid of bacteria and fat. So if I want to isolate the protein, I use ultrafiltration. Then the protein is retained, lactose, minerals, and water will go through. Nanofiltration, I can take the lactose now from a byproduct, and I can use the lactose as an ingredient. So lactose will be my retentate, and minerals and water will go through. Now, if I want to remove the minerals and then purify the water and reuse the water for something else, I run it through reverse osmosis. Yes, Sam. Why would it be retentate with a larger pore size than protein? Because the fat is like they associate. There's the globular. They form, what is it called? The fat membrane or something in milk. So they are not like one molecule. They're agglomerated. Okay. We can do chromatography, obviously, and separate using size exclusion chromatography. This is very commonly used to separate proteins based on their size and run characteristics, determine a ratio of different proteins in a food matrix based on their size, differences in molecular weight. So size exclusion. So the larger molecules will come out first because they won't have access to all pore sizes, whereas the smaller molecules will penetrate in all the pore sizes, kind of like that's why it's also called gel permeation and filtration. So then the smaller ones will be retained and take longer time to elute. It's a very common practice in protein world for isolation, separation, and characterization. Gel electrophoresis is another protein separation, and usually we do it for purposes of characterizing the protein, determining their molecular weight, their distribution. If we hydrolyze the protein to look at the generation of peptides, for example, here's a gel. So larger molecular weight proteins usually don't go through the gel as far as the smaller molecular weight, because again, this is based on gel pore size. So proteins that are small will move down more than proteins that are large. So here, for example, it's a soy protein isolate. And we determine the different components if we run standards on the gel. So these are standard of one type of protein, beta-conglycine, and these are standards for glycine. And we run our sample and we can determine what do we have in this sample. And if I hydrolyze with a specific protein, I can determine which components or protein um, fractions got hydrolyzed. So in this lane here, I can see that the beta-conglycine got hydrolyzed because the band intensity reduced. Whereas in this lane, another enzyme was used that targeted glycine. So I see that the bands for glycine got disappeared, and we have small molecular weight peptides generated. So it's a very powerful tool to look at protein fractions, to look at polymerization, to look at hydrolysis, to look at enzyme specificity here to determine what enzyme breaks down what protein component. So it's a really nice tool. It's not necessarily used to isolate protein and get an isolate. Like it's not used for preparatory or preparation of an isolate. It's mostly used to characterize the proteins. And sometimes we can take that band and take it to LCMS and characterize even more that band, but not really collect a protein concentrate or an isolate from that. So there are different forms of polyacrylamide gel electrophoresis. So that's what page is for. Polyacrylamide gel electrophoresis page. So there are three types of polyacrylamide gel electrophoresis, and the most common one is SDS. So what is SDS? Sodium didosyl sulfate. So this is a reagent. Then when you put it with the protein, it denatures the protein and give it a net negative charge. So it breaks all non-covalent bonds. So SDS is going to break the nature of the protein, breaks non-covalent bond, and adds a negative charge to the protein. So when you run the gel, usually you run a current. So negatively charged proteins are going to go in one direction towards the positive charge when you run the current, negative to positive. So they're all going to go down and separate by size only. The smallest will go down furthest and the largest will be more on the top. And very large proteins will not migrate at all. So if we're looking for polymerization due to processing, we'll see a very dark band at the top. And that would be there's a lot of protein that polymerize and won't go through my gel. So what we usually get is we buy the gels pre-made. So I'm not gonna open it. I usually get a gel that has been expired, but I didn't find an expired gel in our fridge, so I'm not gonna open this one. So basically you buy the gel already pre-made and it would be in a cassette. So it's plastic cassette. Inside of the cassette is your gel and it has wells. So this is a cone here that ha- forces the formation of wells. And in each well, you load your sample. So you inject your sample. Usually it's 5 microliters to 30 microliters, depending on the size of the well. So you inject your sample in these different wells and you put it in the compartment here, this compartment where you put a running buffer. Then you apply the current and proteins start moving down your gel based on their size. So at the end, we usually stain um, the sample. We put um, kind of a marker in there so that we see the line going down and then we know where to stop. We stop the current or the electrophoresis when the blue line reaches the bottom. So we know that everything migrated, we stop it. Now, when we open the plate, we see the gel all colorless. So we don't know where the protein is because it's colorless. All the proteins separated, but we don't see them. So we gently take out the gel and we put it in Kumasi blue gel stain. So we stain it and then we destain it. There's a destaining solution. So the gel then will have a clear background, but only the proteins will react with the dye, with the Kumasi blue. Then we'll see the bands. Nothing else will react with the Kumasi blue. So we don't see anything else. So urea page is basically the same principle, but instead of using SDS, we use urea. Urea will denature the protein, but will not make it carry any other charge. So whatever the charges of the protein is will remain. So the protein will separate based on charge to size ratio. That's how it separates. Urea page is, for example, used specifically to separate casein proteins. Casein proteins are very similar in molecular weight, but they differ in charge. If you run casein proteins on the regular SDS page, they will not separate. So you won't see kappa casein, beta casein, alpha casein. But if you run them on urea page, they will separate. So depending on what proteins you want to run, you might want to use SDS page versus urea page. Native page is when you do not add any detergent and no SDS, no urea, nothing. You just run the protein as is. You don't see much when you run native page because then you don't get good separation. So it's not commonly used. Okay, I ran out of time. All right, so I'll continue on Monday. You guys have a safe Thanksgiving. I'll see you on Monday.